Swayam Prabha. Digital India. Educated India.
Hello and welcome everyone to the last lecture of the series. So what we would be doing today is to finish up on what we started, which is the instrumental variable methods, and recall that what we discussed in the previous class was multiple instruments. So basically we were talking about a situation where we have more instruments than the number of endogenous variables, and very specifically we considered the case of one endogenous variable and multiple instruments. So what we would do today is to start with an example, a simulation example, which will allow you to understand what we learned in the previous section, which is basically that when you have multiple instruments, it's most efficient to take all the instruments and form a linear combination and use that as the instrumental variable. We would also talk about over-identification assumptions or over-identification conditions. That is, when you have multiple instruments, it's possible to test the validity of part of the of a subset of the instruments. So let's start with today's discussion. So what we have first is an example of estimation of demand elasticity for cigarettes. So the question that we ask over here is, how much will a hypothetical cigarette tax reduce cigarette consumption? So naturally what we are saying over here is that we want to estimate the demand function for cigarettes, where QD is essentially the quantity demanded, or you can think of this as the consumption of cigarettes in the market, and price, PCIG, is essentially the price of cigarettes in the market. So what you're trying to compute over here is how does demand change with respect to a change in prices, and particularly the elasticity, right? And that's why the coefficient of interest for us is beta 1, which gives you essentially the elasticity of demand for cigarettes in this case, particularly because remember that because we have this equation, the regression equation specified in log terms, that is log quantity demanded and log prices, hence beta 1 automatically gives you the elasticity and not just dq/dp. So what we are interested in learning is whether the OLS estimator is biased when you estimate this equation using the linear the least square estimator. And of course we have seen before that in a typical demand estimation there is this standard problem of simultaneity biases, because prices are not exogenously given and they are determined as part of the system, and hence the OLS estimations are likely to be biased. So what we look for is an instrumental variable that would help us to overcome this simultaneity bias or any other omitted variable, the bias that we might come across. And so what we do is to estimate this using instrumental variable. So what we have over here is a single endogenous regressor, which is the prices. And so this is just a revised form of the equation that you saw that includes income. So we would just briefly, so for now we would just assume that there is this additional exogenous variable in the regression, but I'll just tell you in a bit why we need to include income in such an estimation. The thing that we need to note over here is that as I said, we are considering the case where we have multiple instruments. So we have Z1I, which is the general sales tax component of prices of cigarettes or the taxes on cigarettes, and Z2I is the cigarette specific tax component for an individual that an individual I faces. Okay. So what we are saying over here is that we are using as instruments the taxes on cigarettes and the general sales taxes on all goods, the logic is that if you increase the taxes, price of cigarettes would increase and hence it would affect demand for cigarettes. However, a tax does not or is not likely to affect the demand for cigarettes directly. It is only going to affect the demand for cigarettes through its effect on prices, and hence tax qualifies as a valid as a valid IV, or it satisfies the assumption of an instrument validity or exogeneity, right. So now we come to the question is, why do we need to control for income? Remember that omitting income in this case means that your taxes, the taxes that you consider, are likely to be correlated with income, because usually states that have higher incomes are also likely to have higher taxes. Now, because income is also naturally correlated with, or very easy to think that income would be correlated with the demand for cigarettes, which means that you have an IV now which is correlated with the excluded income and also correlated with Y. So, which means that your IV, when income is excluded, income will be included in the error term because income is correlated with Y, and the error term in turn would be correlated with your IV's Z, making the IV invalid, right. So, this is in some sense once again what we discussed before, a case of conditional randomization. So, what this means is that when you control for income, Z becomes a valid IV, because conditional on income, Z is independent of the error term UI. Okay. So, let us look at the simulation results of such an exercise. What you have over here is columns showing you the estimate of beta in the previous equation that you saw. In the very first column, it estimates the previous equation, this equation over here that you just saw, the demand for cigarettes on log prices, on the price of cigarettes and income. But the first column does not include income over here, as you see. It only gives you the estimate of beta, okay, beta hat. And this is beta hat IV, where the IV is actually run manually in two steps. In the first step, you regress the price of cigarettes on the two tax components, Z1 and Z2. And in the second step, you use the predicted value of P, which is P hat. In the first column, you are estimating beta hat IV, but remember that in this case we are using a 2 SLS, which means that we are estimating this using the manual 2 SLS estimation, where in the first step you are estimating the prices, which is X, using any one of the IVs that we have, one of the taxes. Let us say we are using Z2, the tax on the cigarette specific tax, or we are using Z1, the sales tax, the specific sales. So, you are using any one of these two IVs manually. So, you predict P hat and then use it in the second stage to estimate beta hat. And what you have is a coefficient estimate of -1, because of course you expect prices and quantity demanded to be negatively correlated, and a standard error of 0.33. In the second column, you do an identical exercise, but note that we are estimating this using IV, meaning that we are correcting for the fact that P hat that you use in the second stage is actually estimated in the first stage. So, you are correcting for the estimation error, and you have the corrected standard errors, and the corrected standard error is more efficient than the incorrect standard error, as we had discussed before. Third column is interesting because now is the first time that we include the income variable, which I said that if you do not include income, the sales tax, the IV, is going to be endogenous in the sense that the IV is going to be correlated with U, because income would be in the error term if you do not include income as a control variable. So once you include income, what you see over here, that the coefficient estimate changes, which is what you would expect, since there was a bias in column 2 and column 1. But once again, what you do here is this estimation is done using only, so all three estimations in columns 1, 2 and 3 are done using only the sales tax as the IV. Now we move on to column 4, where we have used both sales tax as well as the cigarette specific tax. So now what we are doing is we are using a linear combination of the two IVs that we have, and that gives you an estimate which is roughly close to what you had in the previous column. But the most important part to see to note over here is that the standard error estimate is much lower than what you have in the previous column. And remember that the difference between column 3 and column 4 is only the addition of this second IV, which is the cigarette specific tax, and the linear combination of the IV gives you a more efficient estimate. Exactly what we had discussed before, that when you have multiple instruments, valid instruments, it's better to use the all of the valid instruments, because that increases the efficiency, or in other words, that increases the as if random variation in your IV. So given this example, we now move on to the next discussion. In the next discussion related to the case of multiple instruments. So as I said, when you have multiple instruments, it's possible to test for the exogeneity of a subset of instruments, and that is what we generally call the over-identification restrictions. So what do we mean by that? If there is just one instrument for our endogenous variable, we cannot test whether the instrument is uncorrelated with the error. We say that the model is just identified. However, if we have multiple instruments, it is possible to test for the over-identifying restrictions, that is to see if some of the instruments are correlated with the error or not. Or in other words, if some of the instruments are uncorrelated with the error or not. That is, you are testing for the validity assumption of the IVs, of the set of IVs that you have, but as we will see, you cannot test for the validity of all the IVs that you have in case of multiple instruments, but you can test for the validity of some of the IVs or a subset of the IVs. Let us first understand the intuition behind this test, and then we would go on to the formal test. The basic idea is that we have one endogenous variable and two instruments. Then it is possible to compute two different IV estimates, because you have two IVs, and hence you can have two different estimation steps and compute two different beta hats, and these two estimates will not be the same. But if both instruments are exogenous, then the two estimates are likely to be close to each other. So what we are saying over here is the following, that suppose you have two instruments Z1 and Z2, then using each of them, so in the previous example that we had on cigarette demand for cigarettes, the estimation of the elasticity of cigarette consumption, we had two taxes. One was the sales tax and one was the cigarette specific tax. So consider these two instruments, but suppose we are using these two instruments separately, and that gives us two estimates of beta IV, beta 1 IV hat, which is obtained by, let's say, using Z1 as an instrument, and at the same time we can have beta 2 hat IV using Z2 as an IV. Now the point is that because both of these estimates are for the same coefficient beta in the structural equation, which is the relationship between log prices and log quantity demanded for cigarettes, they reflect the same parameter of interest, and hence if the two IVs are valid and relevant, they both must give you the same estimate or close to same estimate, not significantly different estimates. So that's what we are, that's the basic idea, that's the general idea behind the over-identification tests. What it does is, so then what you need to do is, maintaining the validity of one instrument, we can evaluate the exogeneity of the other. So, for instance, in this example that I gave you, suppose we can assume that Z1 is exogenous, which is the sales tax, the generalized sales tax is exogenous. If we maintain that, then we can find out whether this is exogenous or the second IV, which is the cigarette specific sales tax, is exogenous or not. Because if it was exogenous, then beta IV1 must be equal to beta IV2. If it was not exogenous, then beta IV2 is likely to be biased and be different from beta IV1. So that's the principle. If on the other hand, so this is what it says, if on the other hand the two instruments generate very different results, then we have a problem with one or the other of the two instruments or both of them. IV are not the same, then it's more difficult to interpret whether any one of the IVs is valid or not. Right? That also raises doubt about the assumption that you first made, that Z1 is valid, because you cannot be sure whether Z1 is valid and Z2 is invalid or the other way around. Now, implementation of over-identification tests is based on the residuals of the second stage equation of an over-identified model, where the number of excluded instruments, so over-identified model just means that the number of excluded instruments is greater than the number of endogenous regressors. And we will just see how this is done. So, what we saw intuitively on the previous slide, we are just now going to carry this out in a formal regression model, in a formal test, let's say. So, what you start with is a standard equation that you are interested in, the effect of x on y, and beta 1 is the coefficient of interest. And of course, x is endogenous, and that's why you want to use instrumental variables, and you use Z3 and Z4 as IVs. So, you have two instruments and one endogenous variable. So, again we start with the assumption that one of the IVs is valid. So, in this case, let us start with the assumption that Z3 is a valid IV, and we test whether Z4 is valid or not, whether Z4 is exogenous or not. So, first what you do is to run the first stage using Z3 as the instrument, because that's the valid IV we have assumed. So, we run the first stage using Z3, and this gives you an estimate of the predicted value of x. Once you have the predicted value of x, you use that in the second stage regression, okay, which is in the structural model, you replace x by x hat, and this will give you the estimates of beta naught and beta 1, the IV estimates, where you use as IV, recall, Z3. So far so good. So, now once you have beta naught IV and beta 1 IV, so what you have is an estimate of this equation over here, and using those you can compute U1 hat, which is the residual, because you do not know the residuals or you do not observe the residuals. So, what you would be doing is using beta naught hat and beta 1 hat and predicting the residuals. So, U1 hat is the prediction of the residuals using beta naught hat and beta 1 hat, and remember, of course, using x and not x hat, because this is the correct standard error that would or correct residual that we would be interested in. Now, once you have U1 hat, which is basically nothing but this U hat when you use Z3 as the IV, using Z3 as the IV, what is the estimate of U hat is reflected by U1 hat, and then what is the validity of an IV? Validity of an IV is nothing but whether the IV is correlated with the structural error term. So, what you want to test for is whether Z4, which is the excluded IV in this case, is correlated with U or not. So, what you would use is simply this estimate of U1 hat, which is the estimate of the structural residual using Z3 as a valid IV, and regress that on Z4. So, you can also consider this to be a positive sign, it doesn't matter. So you're just running a regression. And this Z4 over here, this means that what you're testing is, you're testing whether gamma 1 is significant or not. So you're testing for the significance of Z4 in a regression with respect to U1 hat, the residual from the structural equation. So this is a test for validity of Z4 as an IV, but it needs to assume that Z3 is a valid IV. So this is very important. You are assuming that Z3 is a valid IV, and based on that you are testing whether Z4 is valid or not. So we cannot actually test for exogenity of all IVs. We still need to maintain the assumption that at least one of the IVs is exogenous, and based on that assumption we can test for the validity of the other IVs. Now what does this mean? It means that you can never be sure whether your starting assumption is right or is a correct assumption to start with. Only on the basis of the idea that your starting assumption that Z3 is valid is correct can you say anything about the rest of the IVs. So what we would do on the next slide is to generalize this idea for multiple IVs, not just two IVs, but when you have a full set of IVs, then what you would be doing is, just to tell you briefly, what you would be doing is that you would be assuming one IV is exogenous at a time and test whether the other IVs are exogenous based on that assumption. And you would do this for every single IV because you cannot be sure. For sure you cannot say that any one of these IVs is a valid IV, and hence we are testing for the exogeneity of the others. So what you do is, every time you take one IV as exogenous and test for the exogeneity of the other IVs, and you do this number of times, as many IVs as you have, and then take a joint statistic and test whether all IVs are exogenous or not based on this procedure. So let's see how it's done. So what you do is regress the residuals from an IV or 2 SLS regression on all instruments in Z. Step 1 is to retrieve the 2 SLS residuals from the second stage regression. That's what you saw in the previous slide, and then regress the residuals on all instruments. So if you have, let's say, 4 instruments, you would be regressing on all the 4 instruments and all the exogenous variables in your model, if you had any exogenous variables. And then what we would be doing in step 3 is to compute a joint test, a joint F test, for testing whether all these instruments are jointly equal to 0 or not. That is, all of them jointly must be uncorrelated with the structural error term which you just predicted in step 2. The over-identification restrictions test the statistic that the J stat, as we say, which is basically M times this F stat, where M is the additional number of instruments that you have. So if you have 3 instruments and 1 endogenous regressor, then M is equal to 2. So under the null hypothesis H naught, that all instruments are exogenous, this J, the J stat, follows a chi-square distribution with Q degrees of freedom. The Q is basically the degree of over-identification, that is the number of instruments minus the number of endogenous variables. If you reject H naught, the null hypothesis, then one of your or more of your IVs are not exogenous. But of course, you cannot pinpoint which IV is exogenous and which IV is not, because you are always having to assume that one is exogenous, and conditional on that assumption, the others are not. This test, under the assumption of IID errors, is often called the Sargan test because it was invented by Sargan. The other concept that we are going to discuss is a test of endogeneity that sort of concludes our discussion of the various tests with respect to IV. And what this suggests is a more fundamental idea that the 2SLS estimator is less efficient than the OLS estimator when the explanatory variables are exogenous. So, what you saw in the when we were discussing IVs and discussing the standard errors with relation to the IV estimation, what you saw was that the standard error of the IV estimation has an R square in the denominator, which, and that's how it differs from the standard error of the OLS estimator. This R square is nothing but the R square from the relationship from the first stage, which is the relationship between X and the IV, X and Z, and that makes the standard error in the IV estimation larger than the standard error in the OLS estimation. So, now if you actually think that your exogenous variables or your explanatory variables are all exogenous, then there is no need to use IVs, because you are anyway going to get unbiased estimates of beta using the OLS estimator. So, what you need to do is to test for the endogeneity of the OLS of the explanatory variable X. So, it is important to test for the endogeneity first in order to avoid using an IV estimator. Why do you want to avoid using IV estimator? A, because IV is computationally more intensive. You are running it in 2 stages as opposed to the linear regression where you have only one linear regression, and it is less efficient. So, the basic idea is the following. The null hypothesis is that beta BIV or beta hat, in other words, what same as B in this case, is same as BOLS. This happens when the covariance between X and the error term is 0, which in other words means that the X is exogenous. So, note that what we are assuming over here is a valid and relevant IV. So, under the assumption that the IV is valid and relevant, BIV is unbiased, and what the first line says is that if BIV is unbiased and is equal to BOLS, this means that BOLS is also unbiased, and then it must be true that X is exogenous and the covariance between X and the error term is equal to 0. Under the alternative hypothesis, BIV is not equal to BOLS, but BIV is unbiased because we have already assumed that IV is valid and relevant. So, then it has to be true that BOLS is not unbiased or is biased because of a correlation between X and the error term. So, under the null hypothesis, BIV and BOLS are consistent, but only OLS is efficient, and under the alternative hypothesis, BIV is consistent, but BOLS is inconsistent. So, if this is the case that we have, then of course we prefer BIV, the IV estimate. But if the first one is the case that we have, then we would prefer BOLS, because in spite of being unbiased, both BIV and BOLS is more efficient. Hence, we prefer BOLS. The Hausman test checks if the difference BIV minus BOLS is statistically different or not. So, is statistically different from 0 or not, that is whether BIV is statistically different from BOLS or not. And by doing this test, what you are saying is that under the assumption that BIV is unbiased, you are checking whether BOLS is unbiased or not. So, the Hausman test statistic is nothing but this difference between the BIV and the BOLS, the variance of this difference and the difference again. So, multiplying the variance of the difference with a square of the difference is what gives you the Hausman test statistic. Under the null hypothesis, this Hausman test statistic H follows a chi-square distribution with k degrees of freedom, where k is basically the number of instrumented regressors or the number of endogenous regressors you are instrumenting. If we accept the null hypothesis, we should use the OLS estimator, because then you are saying that BIV and BOLS are identical and hence X is exogenous. If we reject the null hypothesis, then of course the second case is in is what we have, and then BIV is the only consistent estimator that you have. So how to do this test in a regression equation? So this way you will actually understand what is going on. So start with the structural model, which gives you the relationship between x and y, and suppose that Z3 and Z4 are the IVs that we have. You run the first stage using Z3 and Z4, have an estimate of u from the first stage. The endogeneity of x implies that this error term over here is correlated with u2, the structural error term. So what you want to see is that by including u1 over here in the structural regression, you just want to find out whether u1 and y are correlated or not. But the problem is that neither do you observe u1 nor do you observe u2. So what you do is, in order to test for endogeneity, you first compute the first stage and estimate the residuals u1 hat. You then use the u1 hat in the structural regression and try to see if u1 hat and y are correlated or not. If they are correlated, which means that x is endogenous. If they are not correlated, which means that x is endogenous. The other way around. If they are not correlated, this means that x is exogenous. If they are correlated, this means that x is endogenous. Let us end this lecture series with a discussion of an example, a paper that was written on instrumental variables. So we were discussing instrumental variables. We discussed the properties or the assumptions that an instrument must satisfy. We discussed the case of single instruments. We discussed the case of weak IVs, and then we went on to discuss the case of multiple instruments. And we did all the tests that are possible for in the case of multiple instruments. We could do the over-identification test, and what we ended with in the previous lecture was that in the case of IVs, what you need to do is to first understand whether your x is exogenous or not, because IV is a less efficient estimator. So what we are going to do today is to wrap up this discussion by looking at a specific implementation of instrumental variables in the context of experiments, because you recall that when we started the discussion of instrumental variables, we said that instrumental variables become very important or come in very handy when you have an experiment, but experiments are typically faced with non-compliance problems. So when you have non-compliance in an experiment, instrumental variables can help you retrieve the true causal parameter or the average treatment on the treated, and so this is what we are going to see today in a particular example. So non-compliance makes participation in treatment non-random, and this is where the usefulness of IV comes in. We could use an IV to recover the average treatment on the treated in the presence of non-compliance. So what we are going to do is discuss this paper by Nidhi Pandey in 2013, where she is estimating the impact of mother's welfare program on children's outcome. So what they do is that there have been a number of programs aimed at reducing the welfare dependence of single mother families. These programs usually operate by providing young welfare mothers access to an array of education, employment and family services to increase their human capital, employability and reduce or eliminate their reliance on welfare. So these are sometimes called the temporary assistance to needy families. Now, just generally speaking, what they do is that if you have poor households where there are single mothers, they find it difficult to work and at the same time raise the kid, because it's a trade-off on how you distribute your time between the kid and going to work. But they also need to work because they need to earn income in single mother households, and we are specifically talking about poor households over here. So often governments have this cash transfer schemes for single mother households, but often they also have specific training programs to make these women from poor households who are often very less educated also, to make them more employable. So, this paper actually looks at one such training program, whether the mothers were given various types of training to make them employable. And what they are saying is that they are trying to find out the effect of such programs on the benefit that the children get indirectly, because you have to keep in mind that when such a training program is being given, mothers are away from their children for most part of the day because they are participating in the training program. So, that could bring in some kind of a negative effect. But on the other hand, making them more employable might increase the income of the household, which could have a positive benefit on the children. So, what they are trying to test is the net impact of such a program on children's welfare. So, using a randomized experiment that provided education, training and life skill services to high school dropout mothers as the policy, examining the impact of mothers' participation in the program on their preschool children's cognitive and non-cognitive outcomes. So, both educational as well as behavioral outcomes. So, the question is if whether the program had any impact on children's outcomes. So, where does the identification come from, or how do you estimate the causal, how do you estimate beta causally? The random assignment design of the experiment provides the basis for identifying conditions under which policy induced increases in income, in education and employment among the mothers can help or hurt young children's achievement. So, typically if you want to estimate an equation where you are interested in let us say child welfare and how is that affected by mothers' employment status or opportunity, etc., then the typical problem is that there could be lots of omitted variable biases in this sort of regression when you try to estimate by OLS, and hence the whole idea of randomizing the assignment of or randomizing an IV that would impact mothers' employment but not impact child welfare directly, and that is how you would causally estimate beta or identify beta in other words. So, this particular program is called the New Chance program. The New Chance program. So, during the program's demonstration phase, which began in 1989 and conducted in 1992, New Chance was operated by community based organizations, schools, a community college and municipal agencies at 16 locations in 10 states across the United States. How did the randomization work? Most women enrolled in the program voluntarily. So, they came and enrolled in the program. So, this part was of course endogenous because it was self-selection, though some women were referred by the welfare to work programs. Now, women who applied and were determined to be eligible for the New Chance were randomly assigned to one of the two groups, which are the treatment and the experimental group, which is the treatment group, or the control group. The experimental group could enroll into the program, which is the training program, while the control group could not join the New Chance training program, but could receive other services available in their communities. So, how did the program actually work? The New Chance was implemented in two phases. Phase 1 centered on education, career exposure and a number of services falling under personal development. During this phase, services were delivered at the program site from 9 a.m. until 3 p.m. 5 days a week, with daily attendance at all classes expected. So, this is what I was saying earlier. Note that because if the mothers have to spend so long hours at the training program, they are essentially keeping away from their children, and this could have a negative behavioral effect on the children. Phase 2 services encompassed occupational skills training, and work experience, generally off-site, because they were given some sort of an internship or employment, and ultimately job placement assistance. So phase 2 means that if they get an employment finally, which the program is expected to do, then that would lead to an increase in income and that would benefit the children in turn. The enrollees were permitted to remain in the program for 18 months, throughout which time case managers were expected to counsel them and monitor their progresses. So what the author uses as outcome variables are, remember, these are child welfare, cognitive and non-cognitive skills. And what they use as a cognitive skill is a Bracken basic concept scale school readiness component. So this is the cognitive outcome, and the non-cognitive outcomes are behavioral problems index and positive behavior index, the non-cognitive outcomes. So the idea is that whether the program influenced any of these three measures. So just to give you a rough idea of the sample, more than 50% of the enrollees were African Americans in the US. 60% of the program participants had completed up to grade 10 or even less. This just reflects the two of them together, that we are essentially looking at families who are poor and mothers from such relatively disadvantaged families. Mean comparison tests. So what you need to do first is to see whether the experiment was indeed random. So what you want to do is to compare means across various variables between the treatment and the control groups. And this is what the table does over here. It takes a range of variables: test of adult basic education score, age of mothers at baseline, mother's age at first birth. All of these are likely to affect the child outcome. Percentage of disadvantaged people in the overall sample, dad with family at age 14, etc., etc. So a host of variables over here, depression indicators of mothers and so on. So what they find is that the average in the control group and the treatment group are rarely different from each other, and more importantly, they are rarely or never statistically different from each other. Okay. This establishes the exogeneity of, or the randomness of, the experiment that was conducted. Now given this, therefore any differences between the control and the treatment group that emerged during the follow-up period can be attributed to the program, because there was no baseline differences between the treatment and the control group. So what they estimate over here is the following. They regress the child outcomes Yij, which is a child I and region J, on Zij, whether, so which is the program assignment indicator, whether a mother was assigned to the treatment group, or as which means, in other words, whether a mother was actually asked to join the training program, the New Chance training program, or not. And 0 if the mother is in the control group, which is basically they were given other community services but not asked to join the training program particularly. And then you have all other host of covariates given by Xij, and then you have the geography fixed effects delta J and the error term epsilon Ij. So Xij is a vector of exogenous inputs, includes mother's age, education of grandparents, mother's reading score at baseline, race, etc., etc. So all possible observed variables that could be included and that potentially affects Yij are included in Xij. And the most important variable for us over here is this Zij, which is the program assignment indicator. Now what is treatment on the treated? Treatment on the treated comes from the fact that what we are interested in knowing is whether participation in the program affected children's outcomes. Because it could be, so suppose there is non-compliance. In the presence of non-compliance, what it means is that even if I assign a mother to to a particular treatment, in this case, even if I ask a mother to join the training program, the mother might not join the training program, might not comply with what she has been assigned. But what we are interested in is basically whether if the participation of mothers in the training program affects children's outcomes. So, for the treatment on the treated generated through program participation indicator Dij. So, this is not program assignment, but program participation. So, Dij is equal to 1 if the participation hours in New Chance training program is greater than 0. It is equal to 0 if participation hours in New Chance training program is equal to 0. Then the treatment on treated instruments the program participation indicator with the program assignment. So, what you have is, this is the regression you are interested in because this is program participation, delta Dij is the program participation. What you are interested in is gamma 1, but if there is non-compliance, in the presence of non-compliance, some mothers choose not to participate in the program even when they were assigned the program, which means that there is a choice involved and hence program participation is not entirely exogenous. Hence, what you need to do, and this is where IV comes to a rescue, you need to instrument this variable Dij, the program participation, which is a choice variable, by using the program assignment, which is the exogenous or the random variable, and hence this equation over here, the relationship between Zij, the program assignment, and program participation Dij is the first stage of the IV regression. So, once again, what we have is, we have program assignment and we have program participation. You use program assignment to instrument for program participation, but remember, you could also run a regression of Yij, child outcomes, directly on Zij, which is random, which is exogenous, that is Yij directly on program assignment, which is what we had on the previous slide. Now, this one of course is not giving you the treatment on the treated, but this is giving you something else, the ITT, the intention to treat effect, because this is what I intended the mothers to participate in the program, but they actually did not. So, that is why this pi 1 is called the intention to treat, although of course because Zij is random, pi 1 is going to be unbiased. So, here in this table it gives you the results from the estimation. What you have is, in the first column just gives you the mean of the control group, so that you can calculate the elasticity changes, or you can see how much did it change with respect to the mean value. In the first column you have ITT, so Y regressed on Z, on the IV or on the program assignment, and what you see is that the program positively affected child's BPI score, which is one of the non-cognitive measures, and PBI, which was the positive behavior index, is negatively affected. So, the negative behavior index is positively affected and the positive behavior index is negatively affected, meaning that what this shows is that the intention to treat effect is showing that the program participation or the program assignment had a negative impact on the child's behavior, but no impact on the cognitive skills of the child. Second column gives you OLS estimate, which is the impact of D, the program participation, on Y. But remember, D is endogenous because there is a choice involved in participating or not participating, and hence this is likely to be biased. So, once again you have positive and negative coefficients, but what you need to observe is that these coefficient sizes are different from these in the second column, meaning that these are biased and also measuring something else. Third column is where you use an IV, use Z as an IV for for D. Okay. By using Z as an IV for D, you estimate the treatment on the treated, the coefficient that we are interested in specifically, and what you see is that the treatment on the treated also shows a positive impact of the program on negative behavior and a negative impact of the program on positive behavior on the children. So, we can say that the program had negative impact on the non-cognitive behavior of the children, but no impact on the cognitive behavior of the children. But important thing to understand over here is the difference between column 2 and column 4. Column 2 gives you only the impact of the program assignment on the outcome, but it is not the average treatment on the treated. This is the average treatment on the treated, which you can retrieve by using the IV technique, by using Z or the program assignment as an instrumental variable. So, just to summarize the results that this paper got, the ITT coefficients indicate that children of the treatment mothers have a 3% lower BBCS score, a 2% lower PBI score, which is the behavioral score, and a 1% lower BPI score than the children in the control group. The treatment on the treated also has similar coefficients, but slightly different from the ITT. Two potential reasons for this could be the use of market childcare by mothers receiving the treatment and increase in depression of mothers. So, this concludes our discussion of the instrumental variables and this whole lecture series. Just to summarize what we did in the entire course is basically we started by discussing the benefits or the importance of using causal techniques or estimating parameters causally, the importance of estimating unbiased measures with particularly in the context of microeconomic data. And then what we went on to discuss are two specific problems that we often face when estimating or when using microeconomic data and trying to estimate a relationship between x and y. Those specific two cases were those of omitted variables and measurement error. And then we went on to discuss experimental methods that can be used to retrieve the causal parameters, that is the causal relationship between x and y. We also discussed in the case that we have or in cases where it is not possible to randomize or to actually implement an experiment, because in many cases it is either ethically not possible to implement an experiment or experiments might be too expensive. Then we discussed one method, which is the case of instrumental variables, to see how secondary data can also be used. And in addition, how secondary data can also be used with instrumental variable techniques to also estimate causal parameters. But also what we ended with was a confluence of this experiments and the instrumental variable technique to show that even within experiments it is not always possible to ensure compliance fully. So, in cases where there are non-compliance issues, the instrumental variable technique can also serve to retrieve the average treatment on the treated from the experimental data. Thank you, everyone.